All right, welcome back to the undergraduate seminar, everyone. Daniel Dema is going to give us an introduction to descriptive set theory. I've been looking forward to this talk, and I hope you are too. Yep, take it away, Daniel.
Thank you. Okay, so yeah, hi everyone. So today I'm going to be talking a little bit about descriptive set theory. So I guess just sort of talk a little bit about what descriptive set theory is. Very broadly speaking, descriptive set theory is the study of very nice sets. And I just want to sort of describe its flavor profile a bit. So it's very, I guess, diverse in terms of its flavor. So depending on what you're doing, at times it will feel slightly more like analysis, sometimes slightly more like topology, or sometimes slightly more like just like classical set theory. It's usually like a mix of the three, and of course, depending on what exactly you're doing, it'll typically lean one way or the other. And when I was sort of putting this talk together, it's my hope that you'll sort of get a feel for that diverse flavor profile as we go through. Okay. So just a very rough overview of what we're going to be doing. So I'm going to assume that a good amount of the audience has very little experience with topology. So at first, we're going to talk a little bit about sort of what a topology is and the necessary topology to understand the subject. And then we're going to talk about Polish spaces, which are very nice spaces, as we'll come to find out. After that, we're going to talk about a particularly nice Polish space called the Cantor space and some of its results. And finally, we're going to talk about the idea of measure and category. And we're going to try to use the tools that we'll build up regarding the Cantor space to I guess, talk about a very important theorem. So, yeah, let's get started. So let's talk a little bit about topology. So throughout this presentation, I'm going to be letting X be a set, and we're going to let tau be a topology on X. So I assume some of the audience knows what a topology is. Formally, it's a subset of the power set of X. It contains, the empty set contains X itself. It's closed under unions and under finite intersections. But for those in the audience who haven't taken topology, that might be a lot. So I guess at an intuitive level, what a topology is it gives us a notion of openness on a set. And what I mean by openness is when we think of open sets, we think of sets in which the elements are very nicely packed together. So if you take an element in like an open set, you can find another element in that set which is very, very close to that element. So openness means nicely packed together. And sort of the prototypical notion of openness is like open intervals on the real line, right? And topologies satisfy all the nice properties that open intervals satisfy. Okay. Now, suppose we have some subset D. Okay. And we say that D is dense in X if D intersects any open set. Okay. So that U and tau, what that means, if you see U and tau anywhere in this presentation, that just means U is open in X with respect to this topology. So dense sets are sets which intersect any. Okay. Now we say that our set, or rather space, is separable if it contains a countable dense set. So for example, if you take the real number line with its usual topology, the rational numbers Q, those are dense, all right? Any open interval contains a rational, and the rationals are countable. So R, for example, is separable. We say that X is metrizable if there exists a metric D on X such that our topology tau is equal to the topology induced by D. And what I mean by the topology induced by D is with respect to this metric, you basically take open balls at any point in your space. And if you take unions of these open balls, these give you open sets. So sort of these open balls define what's called a basis for our topology. And we say that our space is complete if every Cauchy sequence in X converges to a point in X. And that's with respect to our specific metric D. So so far, just definitions. Nothing too interesting so far. Oh, it's a bit hard to hear.
Louder, as loud as possible.
Okay. How about now? Is this better? I'll try to shout a little bit louder.
Yeah, much better. Yeah.
Okay, good. Sorry to everyone here.
No.
So, yeah, typical example of a complete space is the real numbers, right? Ours are complete. Of course, they're metrizable. Very nice space. Now, here's a particularly important definition I want to talk about. So say we have a subset Y of X. Okay, so Y is a subset of X. We say that Y is G delta in X if Y can be written as a countable intersection of open sets in our topological space. Okay. So a G delta set is just a countable intersection of open sets. And dual to that notion, we say that Y is F sigma in X if Y is a countable union of closed sets. Okay. So again, G delta, countable intersection of opens, F sigma, countable union of closeds. Okay. I didn't mention what closed means. Let me basically closed just means its complement is open. So if a set is open, sorry, we say a set is closed if its complement is open, vice versa. Okay. So that's a close. And yeah, so in particular, the complement of a G delta set is F sigma. That just follows by De Morgan's and vice versa. And one thing I want to point out is that closed sets are G delta. So let's say Y is closed. Okay. Find the draw tool here. So if Y is closed. I'm sorry about the writing. I'm going to try my best to make it legible. That says Y is closed. And basically what we want to do is we want to take a look at the union for all points X and Y of balls of radius 1 over n, centered at X. Okay. So this notation here just means the radius is like 1 over n for some natural n, and this means it's centered at X, right? So this covers Y, right? It's just a ball around every point, right? And what you can do then, and also, sorry, each of these balls is open, so this entire union is open, right? And then you can look at the intersection of this over every n. Right? So this is a countable intersection of open sets. And this is precisely just equal to 1. So this shows that closed sets are G delta. And similarly, open sets are. So let me just clear that. Okay. So next, what we're going to talk about is this is a pretty dense definition, something called the product. Okay. So now let's say instead of having one topological space, we have some indexed collection of topological spaces. Okay. The size of the index set doesn't really matter. It can be finite, countable, uncountable, whatever you want, right? And basically, we want to give a topology to the product. Right? And the way we do this is we consider these maps called projection maps. So basically, oh my, sorry, the mouse is a little iffy. For each I, we can define a projection map from our product. So I'm going to let X denote the product of all these Xi's. So pi I maps from X to Xi. And all it does is, sorry, I'm having mouse problems. It just sends, I think it's frozen. Oh, no, it's frozen. No, it's not frozen. Okay. It sends X to its ith coordinate. So that's what this projection map is, right? And what we want is we want all of these projection maps for each I to be continuous. So let me briefly talk about what that means. In a topological context, what it means for a map to be continuous is it means the pre-image of every open set. Okay. And I guess for some of the students who are watching this who might not have taken topology before, maybe you've taken calculus and you've seen the epsilon delta definition, right? And in fact, this definition is equivalent to the epsilon delta definition of content. So with that's something nice to think about. But anyway. So we want each of these projection maps to satisfy the condition that the pre-image of every open set is. And so the product topology is the smallest such topology on X satisfying the condition. And what I mean by smallest topology is if you take another topology on X that satisfies that condition, the product topology is a subset of that topology. And basic open sets in X are essentially products of UIs, where UI is a subset of Xi. In particular, each UI is open in Xi, and UI is equal to Xi for all but finitely many. Okay. So, and I guess to sort of explain what I mean by basic open sets is basic open sets are sort of the building blocks of open sets. So open sets are unions of these basic open sets. So for example, if you look at the real number line with its usual topology, R is a union of, open sets in R are unions of open intervals. Open intervals are sort of the basic open sets in R. Yeah, this is analogous to that. So that about wraps up the necessary topology that I wanted to review. Now let's actually get into sort of the descriptive set theory side. So sort of the very natural setting of things in a descriptive set theory is Polish spaces, right? Polish space is a space that is separable. So remember, separable means it contains a countable dense set, and it's also completely metrizable. Okay. And what I mean that by completely metrizable is specifically there exists a metric with respect to which the space is complete. It's not necessarily the case that the space is complete with a specific metric. So I have an example written down here, but so yeah, look at that example, right? If we take the unit open interval, sorry, in R, look at it as a subspace, right? So this is not complete, and the reason it's not complete is, for example, sorry, the mouse is freezing up again. But if you take, like, for example, the sequence of 1 over n, so this is a Cauchy sequence, and this converges to 0. But of course, this interval doesn't contain 0, right? So this is not complete with respect to the usual metric on our case, right? But in fact, there exists a complete metric. So the way we might construct one is using the notion of a homeomorphism. So for those unfamiliar, a homeomorphism is basically the topological analog of an isomorphism. So for example, if you've taken, I don't know, maybe linear algebra, you've seen isomorphisms there. What homeomorphisms do is they basically tell us if two spaces are homeomorphic, then they have the exact same topological properties. Okay. Formally, to show that a function is a homeomorphism, you want it to be a bijection. You want it to be continuous, so the pre-image of every open set is open, and you also want its inverse to be continuous, so the image of every open set is. So formally, that's the definition. Okay. So anyway, say you have some homeomorphism from 0 to R, and if you wanted to construct one, what you'd essentially do is take like some sort of modification of like the arctan function that would do, and you define a metric like so. You send x and y to the absolute value of fx minus fy, and this induces a complete metric. So yeah, by sort of this argument, 0, 1 is a Polish space. Okay. So some simple examples of Polish spaces. Rn for any natural number n, a countable product of R. So this superscript n just means countably many R's. Cn, so complex for any natural n, countable product of C. The n-dimensional cube. So what I mean by that is just an n-fold product of the closed unit interval. So that's a Polish space, and this is of course without our topology. And any countable set with the discrete topology. So for those unfamiliar, the discrete topology is basically just the topology in which every set is. So the power set itself is. So some more special examples of Polish spaces, portable examples of Polish spaces. So first we have the Cantor space, which is denoted with this map calc. And this is the countable product of the set 0, 1. So we have countably many copies of 0, 1. And in particular, this is equipped with the product topology. So this is a topological space. Right? And we're going to talk about this a little bit more in sort of the next section of the talk. There are some very useful embedding results involved in it that I want to go over. So there's also the Hilbert cube. So this is countably many copies of the closed unit interval. And again, this is equipped with the product topology. Another example is the Baire space. So this is with map cal n. So this is countably many products of that itself. Yeah? And again, this is equipped with product topology. And sort of, I want to just comment that with sort of the Cantor space and the Baire space, it's useful to not just think of these as countable products of these sets, but as sequences. So it's useful to think of elements of the Cantor space as sequences of zeros and ones. And similarly as elements of Baire space as sequences of natural numbers. Okay. Okay, so let's talk very briefly about a characterization of Polish subspaces of Polish spaces. So we talked a little bit earlier about how the open unit interval as a subspace of R is Polish, right? And we had to sort of go through the trouble of manually showing that it's complete, right? In fact, we generally don't have to do that because it turns out that Polish subspaces of Polish spaces are just the G delta spaces. And I'm not going to go over the proof of this theorem because it's particularly tedious, but yeah, essentially the beauty of this result is pretty much exactly what I just said. If you have a subset, a subspace, a bigger Polish space, if you want to check if that space itself is also Polish, just check if it's G delta. Okay? Okay, so another nice result. This is an example of an embedding result. I think I might have mentioned that term earlier, embedding, and it'll show up again as we go on. But when we say we want to embed a space into another, essentially what it means is if we look into that space that we're embedding into, we can find a copy of that space that we're embedding. And what I mean by copy is, I mean we can find a homeomorphic copy. So we can find some subset of it that's homeomorphic to the space we're embedding. So that's what an embedding is. And what this result here that we're looking at says is that Polish spaces can be embedded as G delta subspaces. Okay, so again, the Hilbert cube is just better than that. So the Hilbert cube is the countable product of the closed unit. And Polish spaces are precisely just the G delta subspaces of this space, right? And so this result is particularly nice because it gives us sort of another way to think of Polish spaces, right? It allows us to think of them as subspaces of the Hilbert cube, which by itself is a variant space, right? It's Polish, it's compact by Tychonoff's theorem, it's a pretty good space. I won't go into the proof of this, but it's a nice result. Okay, so that pretty much concludes the first section I wanted to go over, which was topology review and an overview of Polish spaces. What I want to do now is talk a little bit about the Cantor space. So first I want to review some terminology. I assume that most of you have probably seen these definitions before, but I wanted to review them again because different texts tend to define some of these differently. So yeah, just for clarity. So let's say we have a topological space, we have a point X in that space. So if as a singleton X is open, we say that X is an isolated point in this space. So points that are not isolated points, okay? We say that a space is perfect if it contains no isolated points. So in other words, all of its points are points. And sorry, the Zoom interface is blocking here. That's fine. We say a point X in a topological space is a condensation point if every open neighborhood of X is uncounted. Okay. So let's talk about the Cantor space. Okay. So maybe I'll review the sort of usual construction of the Cantor set, because what I want to do is I want to really emphasize sort of what I've written here, which is that we can think of the Cantor space as a tree, a binary tree. So if you imagine the unit interval 0, 1, right? The Cantor set is constructed in stages. So at the first stage, we cut out the middle third, and we're left with the left and right third, left and right pieces, right? And at our second stage, we do the exact same thing, but with the pieces we have left. So we cut out the middle thirds of those pieces, and we're left with a left and right piece, right? And we do this again and again for every natural number n, and then we intersect over all the stages to get the campus, right? And let's think about this construction. Basically, sort of two important things are happening at every stage of the construction. So first of all, at every stage, you're essentially going in two different directions, right? So you're either going left or right, left or right. And those two pieces are disjoint, right? So 0 or 1, left or right. Second thing is that every stage is a subset of the previous stage, right? So this is a subset of this. Both of these pieces are subset of these pieces, and so on, right? So sort of even if you look at the picture, you can see how there's sort of a binary tree-like structure. And so thinking of the Cantor space as a tree in this way motivates the following definition: Cantor scheme. So a Cantor scheme on set X is a collection of subsets of X. Let me just explain the notation quickly. So this S less than 2 to the n just means we have a finite string. So a finite string of 0s and 1s. And in particular, so we're indexing sets by strings of 0s and 1s, right? So we're essentially indexing sets by the Cantor set. And the two following conditions here are: if we add 0 or add 1 to S, we get disjointness. So this sort of upwards curve here, this means concatenation. So if we concatenate 0 or we concatenate 1, we get disjointness. And so that corresponds to the disjointness condition that I mentioned when we were constructing the set, right? 0 or 1, you get disjointness, right? And second, if you add, so if you concatenate, then at this stage, you are getting a subset of the previous stage. And that corresponds to the inclusion condition that I mentioned with the construction of the Cantor set. Every stage is a subset of the previous, right? And so what this Cantor scheme does exactly by indexing in this way, what we're doing is we're essentially just mimicking the construction of the Cantor set in whatever space we want. And so the whole point of that is we can use the Cantor scheme as an embedding to prove embedding results. So using Cantor schemes, we can show that we can find topological copies of the Cantor space in other spaces. And this is a super prevalent tool in descriptive set theory. There are a ton of embedding results in it. And pretty much anytime you see embedding involving the Cantor space, you should think to yourself, Cantor space. And there's an analogous definition called a lucid scheme. So I won't talk about it in this presentation, but what it is it's an analogous definition to the Baire space. So rather than just looking at sequences of zeros and ones, you look at sequences of natural numbers. And you do the exact same thing. Give the Baire space a tree structure, and you use these lucid schemes to embed the Baire space. Not directly relevant to what we'll be doing, but just good to know. And here's sort of the picture. So at every stage, we index with a finite string, and we keep going. We add 0 and 1, we get a binary tree. Okay. Now here's a very important result. Let's say we have a non-empty perfect Polish space. So again, perfect means every point is a limit point, right? Then there's an embedding in the Cantor space. And so I'm not going to go over the proof of this, but it essentially just uses a Cantor scheme. So you define a very nice collection of sets, and then you use a Cantor scheme to mimic the construction of the Cantor space. Okay. And we're going to use this result very soon. So a particularly important result in descriptive set theory is this theorem here called the Cantor-Bendixson. So as you can see, what Cantor-Bendixson says is that if you have a Polish space X, X can be uniquely written as a union of a perfect set X and an open countable set X. Okay. And I won't go over the full proof of this, but just to sort of highlight the idea. So the way you define P is just the set of condensation points of X. So P is the set of X such that X is a condensation point. I'll just write con point. Again, sorry about the writing. And you define the set C to be P complement. And then from there, it's just definite. And so as a corollary, using our previous result, we get that any uncountable Polish space contains a copy of the Cantor space, and thus has cardinality C. So let me talk about this little C. So this is read cardinality of the continuum. Okay. So what I mean by cardinality of the continuum is it's just the cardinality of the real numbers. So the continuum is basically a fancy set theoretic name for the size of real numbers. Okay. So that's what that C is.
Sorry, could you go back? Sorry, how's that the consequence of the thing you said before? So we've got perfect and then open and countable, but how's this corollary of Cantor?
So basically this P is perfect.
Okay.
So in particular,
It's Polish. Oh, so then
Perfect
that thing is the thing
yeah,
that contains
exactly. Perfect is closed, so it's G delta. So by our earlier characterization, it's Polish.
Okay. Cool. Nice.
The Polish space can only have a maximum cardinality of the P, because you only talk about how Cantor says a subset of could it like contain too much more stuff.
Yeah, I think this is a lower bound under now. I don't think you're gonna have an upper bound.
Maybe I'll go back to that. That's fine. Yeah, no, we can go back to that. Okay, so let's talk about Borel sets. So Borel sets are a very special class of sets. Maybe before talking about them, I'll introduce this definition here. So let's say we have a set X, right? And we take a collection of subsets of X, which we'll call M. So M is a subset of the power set of X. We say that M is a sigma algebra on X if it satisfies the conditions that it's closed under countable unions. So any countable union of, if you take a countable collection of sets in M and you take their union, that's also an M, and it's closed under complements. So you take a set in M, it's complements. So satisfying those two conditions, we say that it's a sigma algebra. Okay. Now let's say we take a subset of the power set of X, which we'll call A. We refer to the smallest sigma algebra containing A as the sigma algebra generator. So it's if you wanted to construct it explicitly, it's the intersection of all sigma algebras. Now, the class of Borel sets, topological space X, is the sigma algebra generated by the open sets of X. So it's the smallest sigma algebra containing all open sets of X. Okay. And Borel sets are a sort of very nice topic. In particular, Borel sets sort of stratify into a hierarchy called the Borel hierarchy. And that's a pretty complicated topic, which I won't get into in this talk because it deserves a talk of its own, but just something useful to know. So we have this very nice theorem here for polar spaces and Borel sets. So what this result says, if we have a Polish space X and we take a Borel set A in X, then there is a Polish topology. So what I mean by Polish topology is if you take the set with this topology that is Polish with respect to this topology, we'll call tau A. And this Polish topology tau A extends tau. So tau is a subset of this new Polish topology. And in particular, despite extending this topology, the Borel sets generated by this topology are the same as the Borel sets generated by our old topology. So we've made our notion of openness bigger in some sense, but our Borel sets stay the same. And in particular, A is cloping. So it's both closed and open. And the proof of this is like a little bit complicated as well, but sort of the idea, which I thought was very cool, is you consider the class of all sets that satisfy this condition. And let's say we call that set S, and basically it suffices to show that S is a sigma algebra and that it contains tau. So I thought that was a very cool proof idea, but it's also a little bit more complicated, but that's and that just plays on the fact that because we're working with Borel sets, everything's closed under unions. And sorry. Anyway, yeah. So we're going to make use of this result now in what we call the perfect set theorem for Borel sets. So let's say X with tau is a Polish space and A is an uncountable Borel set. Okay. Then A itself contains a copy of the Cantor space. So here's the proof. By the theorem we just discussed, we can first extend tau to a topology tau A, in which A is cloping, and Borel sets of tau A are Borel sets of tau. Okay? Now, since A is cloping, it's closed, right? Because it's closed, it's G delta. Remember earlier we talked about how closed sets are G delta. Now, it's G delta, and it's a subspace of Polish space. So by our characterization for Polish subspaces, Polish spaces, it's Polish. So A is uncountable and Polish. So by the Cantor-Bendixson theorem, A contains a copy of the Cantor space. So this here, we haven't really done anything. This is just a very nice gathering of all the results we discussed. So now we're going to move on to the last section of the talk. This is going to revolve around the notion of measure category. Okay? So I'll talk about what those are. So let's say we have a subset A of R. So we say that it has Lebesgue measure 0, or that it's a null set if for any epsilon greater than 0, you can find a countable collection of open intervals, which cover, meaning A is a subset of the union of those intervals, and the sum of the lengths of those intervals is less than 0. So sort of the intuition there is that sets of Lebesgue measure 0 or null sets have negligibly small volume. Another definition. So let's say we have a subset U of 1. If its closure has empty interior, then we say that U is nowhere dense. And we say that a subset A in R is meager if it's a countable union of nowhere dense sets. So nowhere dense means closure has empty interior. Meager means countable union of nowhere dense. Okay. And so one thing I want to point out is that null and meager are respectively analytical and topological notions of small sets. So when you're doing analysis and you think of small sets, you think of null sets. When you're doing topology, you think of small sets, you think of meager sets. And it's particularly important to note that meager is a topological property. So being meager is preserved by homeomorphism. But being measure 0 or null is not a topological property. So you can find two spaces that are homeomorphic, but one has measure 0 and the other. So one example is there are different variations of the Cantor space, which are homeomorphic, but one has measure 0 and the other has positive. It's something to be aware of. Okay, so I want to talk very briefly about the notion of Baire category. Okay. So I'm just going to very briefly point out, if you ever hear the word category in this presentation, please don't think of like categories as in category theory. This has nothing to do with category theory. This is Baire category. Okay. So this is just a naming. So if A as a subset of R is meager, it's said to be a first category. And if A is meager, it's said to be a second category. Okay? Now, we're not going to use this convention because I think it's confusing. Sometimes I mix the two up myself. And so yeah, I just wanted to make that remark very. So on the notion of category, we have a very important result called the Baire category. Okay. So I've written these three conditions here, and I won't read them all out because they're all on the slide. But if you look at these three conditions here, they are equivalent. Okay? And I'm not going to prove that they're equivalent. But essentially what the Baire category theorem states is that if you have a completely metrizable space X, then it satisfies all three of these equivalent conditions. And depending on sort of the reference that you're using, you'll only see like one of these conditions or the other. Personally, the one I like most is this third condition here, that the intersection of countably many dense open sets of X is dense. So yeah, we're going to discuss the proof of the Baire category theorem with respect to this condition. So let's let X be completely metrizable, right? Let's take a collection of countable dense open sets. Okay? So we'll call this collection UN, and we want to show that the intersection of UN is dense. Meaning, if we take an arbitrary open set UNX, then this intersection intersects. Right? So remember, each UN is dense, right? So in particular, U1 is dense. And what that means is that the intersection of U1 and U is not empty, right? So we can pick a point inside U1 intersection, right? And U1 intersect U is also open because an intersection of two open sets is open, right? So U1 intersect U is open. So around this point in U1 intersect U, we can construct a sufficiently small called B1 centered at that point. And in particular, it's sufficiently small so that it's contained in the intersection and its closure is contained in the intersection. And one thing that I'll mention that I didn't write here, we want it to be so small that its radius is less than 1/2.
Okay. So like, yeah, BN should have radius less than 1/n.
Yes.
Or less than, yeah. It's like really, really, really small. Fast enough for this thing.
Exactly. That's it. So, okay. So then we have a B, right? U2 is dense, so B1 intersects U. B1 intersects U2, right? So we can do the same thing. We can construct a smaller B2, which is contained in the intersection of B1. And again, we want its closure. And we want its radius to be less than 1, right? And we can repeat this process inductively. So at the nth step, we want the radius to be less than 1/n. And then what we can do is we can look at the center points of the sequence of balls, right? So because of how we've chosen our balls, we've chosen them to be specifically small, sufficiently small. The sequence of center points is a Cauchy sequence. Because the sequence is Cauchy, it converges to a point in X, which we'll call little x here. So that's just by completeness. Now, by construction, little x is contained in the intersection of all these BNs, right? And that's contained in the intersection of all these UNs with U, right? And we've done exactly what we wanted to do. We wanted to show that the intersection of these UNs intersect. So that concludes it. Okay? That's the proof of the Baire category. So let's talk a little bit about something called the continuum hypothesis. Up again. So, just a little bit of notation in this definition. In set theory, there's this idea of these left numbers, right? So this symbol here is called a left knot. And a left numbers basically just represent cardinalities. So a left knot is defined to be the cardinality of n. So countable sets are those which have cardinality less than or equal to the Now, those which don't satisfy this condition are said to be uncountable. And in particular, we denote the first uncountable. Okay. So now let's talk about the continuum hypothesis. So the continuum hypothesis, denoted CH, is the statement that the cardinality of the continuum is to the left. Or equivalently, that if you take any uncountable subset of R, then it has cardinality. Now, CH is really interesting because it's independent of ZFC. So for those unfamiliar with ZFC, ZFC is the collection of axioms of set. So it's the axioms that we all canonically assume when we're doing mathematics. And what it means for CH to be independent of ZFC is if you assume CH, then CH in consideration, all the axioms of ZFC has no contradictions. So in some sense, it's compatible with these other axioms. But its negation is also compatible with these other axioms. Whether you assume CH or not CH, no contradictions. Now, here's sort of the main theorem that I wanted to discuss. So This is sort of a duality of the relationship between measure and category, which sort of gives us a relationship between analytical and topological notions of smallness. So let's assume CH, okay? And let's say phi is some sort of statement of subsets of R, and let's say it involves notions of Lebesgue measure 0 and. So let's say we take another statement, which we'll call phi dual, which is just phi with this asterisk. So let's say phi dual is the exact same statement, except we replace all occurrences of Lebesgue measure 0 with meager and vice versa. Then what happens is phi holds if and only if phi dual holds. And the reason that this is the case is thanks to this nice result here. This is called the Erdős-Sierkinski duality. If we assume CH, then there exists a bijection F from R to R, such that for any subset A of R, A is null if and only if the image of A is meager, and vice versa. So F interchanges meager and null sets.
It's insane. It's a ridiculous thing that only Erdős sequence you would do.
Do we need any stronger conditional F, for example, it is continuous homeomorphism?
So
Because the bijection seems to be just, it might be just randomly
yeah,
scrambling points. And
I don't think if I'm actually not sure if we know any like properties of F because the proof is like it's very strange. I assume it's
going to be
some sort of,
non,
like, very monstrous.
yeah,
right?
it's going to be,
I don't know if it has any properties.
well, for one thing, it's going to be very non-constructive.
Yeah, it's very.
You
I can only assume it's not a very nice function. And yeah, so the proof of this theorem is pretty complicated, deserves a talk of its own. So I'm not going to go in depth of the proof of this theorem, but rather what I want to discuss is some lemmas that are used.
So keep in mind, you've got like 8 minutes, right? Like we're getting close to the end.
We are, yeah, the last 2 slides.
Okay, cool.
Okay. So our first lemma is that you can decompose R into a null and meager set. And so this doesn't really use any like super interesting tools, but I wanted to talk about it because this is a very useful little trick. So essentially what you do is you enumerate the rationals. You can do that because the rationals are countable, right? We'll call the rationals Qi, and we'll take n to be a natural number, and we'll define a set Un to be the union over all i's of these open intervals centered at each Q. And we go left 1 over 2 to the I plus n, and right 1 over 2 to the I plus n. Now, you can see that this is a bounded set, right? And as n goes up, this gets smaller and smaller, right? In particular, as n goes towards infinity, this just approaches 1. So let's take the intersection over n of all these n's. Now, what ends up happening is, if we look at the length of these intervals, the length of these intervals is to 0. Right? And using a nice little result from measure theory, what ends up happening is the measure of this intersection is the limit of the length, which is just 0. So the intersection of all these UNs has measures. So this is a null set. And if we just take its complement, so let's talk about another lemma. This is the last lemma, last couple of minutes. So let's say we have some null and meager respectively subsets of R, which we'll call F and G. So F is null, G is meager. And there exists a null set F plus, which contains F, and a meager set G plus, which contains G. And the difference in our extension, so F plus minus F, so the difference in the extension has cardinality of the container. And the difference in the extension of our meager set also is cardinality. So let's try to prove this. So without loss of generality, F is F sigma. So let's talk about that here. We know that F is sorry, this should say G is F sigma. This is a typo. This should say G. Sorry about that. So without loss of generality, G is F sigma. And so the reason for that is we know that G is right. And if we think about a meager set, it's a countable union of nowhere dense sets, right? And in particular, that means the closure of each set in that intersection, in that union, has empty interior, right? Now, say we take the closure of each of those sets in the union, right? Then what ends up happening? Well, the set itself is then closed, right? But then the closure of closure is just itself, right? So in particular, what we're going to do is we're going to just take the closures, and we still have meagerness. And the reason why this sort of doesn't bother us is because all we're doing in taking closures is we're just making the set bigger, right? So we're not losing meagerness, but we're making the set bigger. And then what we're going to do is we're going to look at the complements. Okay? So we have that G is F sigma. And so because G is F sigma, the complement of G is G delta, right? So because it's G delta, remember G delta subspace is a Polish space of Polish. So the complement of G is Polish. And it's co-meager, meaning that it's complemented, right? So G is meager, so G complement is co-meager. And so because it's Polish and co-meager, it's uncountable by the Baire category.
So we're running into question period time, and I will have to stop you soon because there's like admin stuff to do. So when we get to the end of maybe this part of the sketch or something, we should probably take a break.
Sure. Yeah, I'll just finish this slide because this is the last. So using the Baire category theorem, we get that the set G complement is uncountable. Because it's uncountable in Polish, it contains a copy of the Cantor space by Cantor-Bendixson. So we can just define our set F plus to be F with the union of our copy of the Cantor space. And yeah, so this F union some set in the complement, so it contains that for sure. And the Cantor space has cardinality of the continuum, so right. Now we do something similar with our set. Sorry, this is F. This is the other typo. Without loss of generality, we can assume F is Borel. So you can show that any null set is containing a Borel null set. So that's the reason why this. And because F is Borel, so is F complement, right? And it's also uncountable because any null set, any countable set is null. So any non-null set is uncountable. So F complement is Borel. So by the perfect set theorem, it contains the copy of the Cantor space. But remember, being measure zero is not preserved by homeomorphism. So we can't just do the exact same thing we did before with meagerness. So what we need to do is we need to do a little trick. And the trick we're going to do is we're going to take a countable dense set inside our copy of the Cantor space. And the reason we can do that is because separable subspaces, separable metric spaces are separable. And we do the exact same little trick we did before, where we take these decreases, and then we take the intersections of our UNs, we union that with G, and that's our desired message. Sorry about the typos there. And yeah, that's it. So
Sweet. Okay, I'm going to put a little bit of stuff in the chat for people who are online. So thank you for that chat. Yeah, this maps.
thanks, Paul.
Right here.
Well, please enjoy this.
So for folks who are online, please fill out this seminar feedback form. This gives feedback to our speaker. If people have to go now, it's 2:00. So I hope you have a lovely afternoon. Next week, we've got a speaker, Adib, who's going to tell us about linear algebra and neural nets and the brain and stuff. We've still got the room booked. If people want to ask questions of Daniel, we're still here, but please, please, please fill out that form to get some feedback today. So thank you very much. Are there questions for Daniel at all? Either speak up or put something in the chat.
So on one slide you had the union of the, I think it was the perfect set, like P union C, and then later on you talked about just the slide before this, F union G, where F was null and meager. Does this decomposition have some kind of, I guess, are they analogs in some way? Right, yeah. So how R can be decomposed into a null and meager set, and how earlier you had the I think it's like the cupcake theorem is what it's called.
Oh, I see what you're saying.
Yeah.
That's a really good. Basically, we think about R as Polish, right? So we can write R as like so, right? Off the top of my head, I want to say no, but we essentially have to just double check the properties here, right? So like, if we look at the set F, this is section.
Yeah, I doubt that like F is perfect and G is whatever properties C has, but that was I found that to be like a cool observation. Maybe there's some sort of connection there.
Think about it and I'll get back to you.
Yeah, thanks.
Other questions, other things people want to ask while we're still here? I have a question.
Yeah, that was the earlier when we were talking about like how was it the set is a union of P and C. Yeah. Right, and then P being uncountable. So just
Correct. So it's here, right?
yeah. I'm not really familiar with topology, so
Yeah.
yeah, I'm gonna take it like maybe next turn.
So yeah, your question was like, this thing has cardinality C, but could it a cardinality continuum, but could it have like bigger cardinality than continuum? Or does the whole space actually have to have cardinality continuum?
So we know the anchor size inside of P, but what about the
No, it's exactly correct. It's not just I don't remember the justification for that.
Oh, but that's
Is it that all Polish spaces embed in something that's cardinality continuum?
Yes, so maybe if we think of Polish space as
it's embedded in
it's G delta and Hilbert cube.
Yeah, so Hilbert cube
Hilbert
is
cube.
definitely uncountable, or definitely has cardinality continuum. So you know that the cardinality is at least C, or sorry, at least continuum, and then you know it's at most because of this embedding.
Yes.
There's more stuff coming in the chat. It's existing.
if you don't have CH, then yes, it's
Oh.
going to fail, and here's how.
So this is without CH, right?
Yeah.
Yeah.
So yeah, so you really need a continuum hypothesis to build this thing.
Not quite. So basically, like, I don't actually have the entire proof memorized, but the role that CH plays in the proof is basically you use it to index. And at some point you take unions of these indices of ordinals less than -1. And so each of those are countable, so you take countable. And so basically what you do in the proof is you take countable unions of nulls and countable unions of pairs, and those are still null by CH because countable. And so that's the role that CH actually plays. But there are actually weaker assumptions that will still give you that. So like something that shows set theory is something called like additivity of an ideal sets. And basically the additivity of the set is the smallest cardinal at which the union is no longer contained in that idea. So for example, the additivity of null sets is the smallest cardinality such that if you take a union of that many null sets, it's not necessarily null.
Right.
So the assumption you would make that would allow this to still hold is that the additivity is equal to continuum for null. So that's actually weaker.
Well, if there's no more questions, we'll end the call here. That was awesome. Thank you for that. Thank you for coming out. We will see you again next week. Yeah, be well, everyone. So,